Here are solutions to homework set number 1 for ECE 376. Now this table is kind of a summary of the different solutions. We'll go through them one by one. The first problem is if you go to Bison Academy, you can look up under whole old homework sets and solutions. From spring 23, the first problem tells you how long it takes to measure to drive the LCD display. That was 6.2 milliseconds. And we'll be doing that a little bit later when we get to homework set number 9 this semester. Similar things. Problem 2 is if the PIC can drive 25 milliamps, how much resistance do you need on each output pin? And there you have V equals IR. I've got the voltage, the PIC output's 5 volts. I can do 25 milliamps times R. So R has to be at least 200 ohms. That's important. Whenever I connect a load to the PIC, it's got to be at least 200 ohms. If it's less than that, typically add a 200 ohm resistor in series, just to make sure it draws less than 25 milliamps. On to problem 3. So for problem 3, if I have this circuit right here with R1 and R2, if R2 is 3300 ohms, what is the voltage? So by voltage division, I get R2 over R1 plus R2 times 5 volts. This is going to be 3.83 volts. And that's the analog input on the PIC, can read 0 to 5 volts. The resolution is 4.88 millivolts. So if this changes by 4.88 millivolts, changes to 3.842 volts, then the resistance, recalculating R2 becomes 3318 ohms. So the difference is it went from 3300 to 3318. So that's 18 ohms. That's the resolution. This right here is an ohm meter, and I can read 3300 ohms with a resolution of 18 ohms, or about 0.5%. If instead I take the resistor R2, make it a thermistor, that's a temperature-sensitive resistor, where the resistance is a function of temperature. At 3300 ohms, you plug that in for R2, solve backwards, and you wind up that temperature is 0.116 degrees Celsius. Actually, what the thermistor looks like, it's resistance versus temperature. At 25 Celsius, that's 298 Kelvin. These cancel, e to the 0 is 1. So at 25 Celsius, it's at 1 kilo ohm. If it goes up to 3.3 K, the temperature is less than 25. Turns out to be 0.11 C. The second part of problem 4 is how much does the temperature have to change for the resistance to change by 18 ohms, for the A to D to change by 4.88 millivolts. So if I go back to 3318 ohms, the smallest change in resistance that I can measure, the temperature corresponds to 0.011 degrees Celsius. So comparing these two, the difference in temperature is the difference in the two, 0.104 degrees Celsius. So with the analog input, I can read temperature to 0.1 degrees Celsius. Problem 5 looks at the PIC in terms of timing. The PIC can measure time, 200 nanoseconds. That's a really small amount. To give an idea what that means, the fastest animal is the peregrine falcon, flies 320 kilometers an hour. In 1 clock, 100 nanoseconds, it'll fly 8.8 microns. Human hair is about 180 microns, so that's a lot less than a human hair. If I build a 555 timer, what happens is I charge the capacitor through R1 and R2, I discharge through R2, and I get kind of like this. That's the voltage at the capacitor. And the output is a square wave. The period of the square wave is a function of R1, R2, and C, follows this equation. If you set this up as R1 is 1K, R2 is 3.3K, C is 0.1 microfarad, the period is 526 microseconds, or 1898 hertz. I can use this to measure resistance. If I let R2 be an unknown resistance, nominally 3,300 ohms. If the resistance changes, the period changes, and the PIC can see that. They can measure time to 100 nanoseconds. So problem 7 says, well, suppose the time, or how much does the frequency have to change for the period to increase by 100 nanoseconds? So here's the period, nominally, 1897 hertz. If I add 100 nanoseconds, this goes from 526.8 microseconds to 526.89 microseconds. The frequency changes. The difference in frequency between the nominal 1898.28 and this one 1897.92, the difference is your resolution. So if I measure time, I can measure 3,300 hertz with a resolution of 0.3 hertz, or 0.1%. Kind of rule of thumb, if you convert something to time, the PIC can measure it really accurately. Number 8 says, suppose that resistor R2 is a temperature sensor. How much does temperature have to change for the time the period to change by 100 nanoseconds? So again, here's the equation for the period. The nominal period is 5.26792 microseconds. If I add 100 nanoseconds, so that 7 becomes an 8. Recalculate R2, then if CB remains 0.1 microfarad, R1 remains 1,000 ohms. R2 has to change to 3,300.72 ohms. So change of 0.72. What this means is a PIC can measure 3,300 ohms with a resolution of 0.72 ohms if I use a 555 timer, or if I convert the resistance to time. Again, the PIC can measure time really accurately. So that's homework set number 1. Just kind of give you an idea, what does 4.8 millivolts mean? What does 100 nanoseconds mean? The PIC we're using isn't the world's most powerful processor, but it's really impressive. I can measure temperature, pressure, resistance, voltage fairly accurately. And that's homework set number 1 for 376.